Lesson L017, AI Ethics and Society.
Welcome to Lesson 17, where we examine the ethical and societal dimensions of artificial intelligence. This is perhaps the most important lesson in this entire course because the technical capabilities we have discussed mean nothing if the systems we build are not aligned with human values. We will cover algorithmic bias, fairness, accountability, transparency, privacy, job displacement, AI governance, and regulation, all illustrated with real examples and a balanced perspective. Let us begin with algorithmic bias, which is arguably the most visible ethical challenge in AI today.
Algorithmic bias occurs when an AI system produces systematically unfair outcomes for certain groups of people. This bias typically enters through three pathways. The first is biased training data. If historical data reflects existing societal prejudices, the model will learn and amplify those prejudices. The second is biased labeling, where the people creating the training data introduce their own conscious or unconscious biases. The third is biased problem formulation, where the way a question is asked encodes assumptions that disadvantage certain groups. A stark real-world example is the compass recidivism algorithm used in the United States criminal justice system. A 2016 ProPublica investigation found that the algorithm incorrectly labeled black defendants as future criminals at nearly twice the rate as white defendants. Conversely, it incorrectly labeled white defendants as low risk more often than black defendants. The company that built Compass defended the system by pointing out that it achieved similar accuracy rates across groups, illustrating a fundamental tension in algorithmic fairness where different definitions of fairness can conflict with each other. Another prominent example is biased hiring algorithms. In 2018, Amazon scrapped an AI recruiting tool that systematically penalized resumes containing the word women or that mentioned all women colleges, because it was trained on predominantly male resumes from the tech industry. Image recognition systems have also shown significant bias. Researchers found that commercial facial recognition systems had error rates of less than 1% for white men but up to 35% for dark-skinned women. In 2020, the Detroit Police Department wrongfully arrested a black man named Robert Williams based on a faulty facial recognition match, demonstrating that algorithmic bias is not a hypothetical problem but a present-day reality affecting real people. This brings us to the concept of fairness in AI, which turns out to be surprisingly difficult to define precisely. Computer scientists and philosophers have proposed multiple mathematical definitions of fairness, and many of these definitions are mutually incompatible. The impossibility theorem of fairness, proven by John Kleinberg and colleagues in 2016, demonstrates that unless base rates are equal across groups, it is mathematically impossible to simultaneously satisfy three intuitive fairness criteria. The first criterion is demographic parity, which requires that a decision is made independently of membership in a protected group. The second criterion is equal opportunity, which requires that qualified individuals from all groups have an equal chance of being correctly identified as qualified. The third criterion is equalized odds, which requires that both false positive rates and false negative rates are equal across groups. Because you cannot satisfy all three simultaneously unless base rates happen to be identical across groups, any fairness-aware AI system involves a value judgment about which type of fairness matters most. There is no purely technical solution to this problem.
It requires ongoing dialogue between technologists, affected communities, ethicists, and policymakers. The field of fairness in machine learning has grown rapidly in response, with researchers developing tools like IBM's AI Fairness 360 Toolkit and Google's What If tool, which allow developers to audit their models for bias and experiment with different fairness constraints.
Accountability is the next pillar of AI ethics. When an AI system causes harm, who is responsible?
This question becomes urgent as AI systems are deployed in high-stakes domains like healthcare, criminal justice, and autonomous vehicles.
In 2018, an Uber self-driving car struck and killed a pedestrian named Elaine Herzberg in Tempe, Arizona. The safety driver was charged with negligent homicide, but the company itself faced no criminal charges, raising questions about corporate accountability. In healthcare, if an AI diagnostic tool misses a tumor, the liability chain is similarly unclear. Is the doctor who relied on the AI system responsible? Is the hospital that deployed it responsible? Is the AI developer responsible?
The European Union's proposed AI liability directive attempts to address these questions by shifting the burden of proof in certain cases, so that if an AI system causes harm, the victim only needs to show that the system failed to comply with requirements, and the burden then shifts to the provider.
Another important accountability mechanism is human oversight.
The concept of human in the loop, where a human must approve each AI decision, and human on the loop, where a human monitors decisions and can intervene if necessary, are both being codified into regulation. However, research on automation bias shows that humans tend to trust automated systems even when those systems are making mistakes, meaning human oversight is not a perfect solution.
Transparency and explainability are closely related to accountability.
If we cannot understand why an AI system made a particular decision, how can we determine whether that decision was fair or correct?
Modern deep learning models are often described as black boxes because even their creators cannot fully explain their behavior.
The field of explainable AI, or XAI, aims to address this by developing techniques for model interpretability. One popular approach is SHAP, which stands for Shapley Additive Explanations. SHAP values are based on cooperative game theory and tell you how much each input feature contributed to a particular prediction. If a loan application is denied, SHAP can show that the applicant's income level contributed negatively while their credit history contributed positively.
Another approach is LIME, which stands for Local Interpretable Model Agnostic Explanations.
LIME works by perturbing the input slightly and observing how the output changes, building a simple interpretable model around each prediction. For image classification, LIME highlights which pixels in an image were most important for the model's decision. While these tools are valuable, they have limitations.
Explanations can be misleading or incomplete, and there is debate about how much explanation is truly necessary.
The European Union's GDPR includes a right to explanation, requiring that automated decisions be explainable to affected individuals, but the exact interpretation remains contested in practice.
Privacy is another critical concern in AI ethics.
AI systems typically require vast amounts of data to train effectively, and this data often includes sensitive personal information.
Consider facial recognition systems deployed in public spaces.
Cities like London, Moscow, and Beijing have extensive networks of surveillance cameras connected to facial recognition systems. In London alone, there are over 600,000 CCTV cameras, many of which are AI-enabled. Privacy advocates argue that this widespread surveillance has a chilling effect on public life, discouraging dissent and protest. Differential privacy is a technical approach that attempts to allow AI training while protecting individual privacy. The idea is to add carefully calibrated noise to the data or to the training process so that the model learns statistical patterns without memorizing information about any specific individual. Apple uses differential privacy to learn popular emoji usage patterns and typing habits without knowing which specific user typed what. Another important technique is federated learning, where a model is trained across multiple devices without the raw data ever leaving those devices. Google's Gboard keyboard uses federated learning to improve its next word prediction model without uploading users' typing data to Google servers. Only the model updates, not the raw data, are sent to the central server. Despite these technical advances, privacy remains a fundamental challenge that requires strong legal frameworks and organizational accountability alongside technical solutions. Job displacement is perhaps the concern about AI that most directly affects the general public. A 2017 study by McKinsey Global Institute estimated that by 2030, up to 375 million workers worldwide, or roughly 14% of the global workforce, may need to switch occupational categories due to automation. Jobs that involve routine, predictable tasks are most at risk, including manufacturing assembly line work, data entry, retail cashier positions, and even white-collar jobs like basic accounting and legal document review.
However, AI also creates new jobs.
The World Economic Forum's 2023 Future of Jobs report estimates that while automation will displace about 83 million jobs by 2027, it will also create about 69 million new ones.
New roles include AI ethicists, prompt engineers, data labeling specialists, and machine learning operations engineers. The more nuanced question is what kinds of jobs will be created versus destroyed. Many of the new jobs require technical skills that displaced workers may not have, raising important questions about education, retraining, and social safety nets.
Some economists advocate for universal basic income as a response to AI-driven displacement, while others emphasize retraining and education. The historical record offers some grounds for optimism. When ATMs were introduced in the 1970s, many predicted the end of bank tellers. In fact, the number of bank tellers increased because ATMs reduced the cost of operating branches, leading banks to open more branches and hire more tellers for customer service roles. A similar pattern may play out with AI, where the technology augments human workers rather than replacing them entirely, though the transition period will be disruptive for many.
AI governance and regulation are the frameworks we use to ensure responsible development and deployment. Currently, there is no single global framework, but several major initiatives are underway. The European Union has been the most aggressive regulator. The EU AI Act, approved in 2024, takes a risk-based approach, categorizing AI applications into 4 risk levels. Minimal risk applications like video game AI face no additional requirements. Limited risk applications like chatbots must comply with transparency obligations. High-risk applications in hiring, credit scoring, law enforcement, and access to essential services face strict requirements including risk assessment, documentation, human oversight, and accuracy testing. Unacceptable risk applications like social scoring systems and real-time biometric surveillance in public spaces are banned outright. The United States has taken a different approach, favoring voluntary commitments and sector-specific regulation. In 2023, the Biden administration issued an executive order requiring developers of powerful AI systems to share safety test results with the government and directing the development of standards for AI safety and security. However, this order could be reversed by a future administration. China has required AI systems to align with socialist core values and imposed strict content controls on generative AI. These different regulatory philosophies reflect different cultural values. The challenge for global AI governance is to create international standards while respecting legitimate differences in national priorities. Organizations like the OECD and the United Nations are working on international frameworks, but progress is slow. Maintaining a balanced perspective on AI ethics is essential. AI is not inherently good or bad. It is a technology that can be used for beneficial or harmful purposes, and often the same technology has both positive and negative effects simultaneously. Facial recognition can help find missing children and also enable mass surveillance. AI in healthcare can diagnose diseases earlier and also encode racial bias in treatment recommendations. The goal of AI ethics is not to stop technological progress but to guide it in directions that maximize benefits while minimizing harms. This requires diverse voices at the table. Currently, the AI field is overwhelmingly male and predominantly white and Asian. A 2019 study found that only 15% of AI researchers at Facebook and 20% at Google were women. Only 2.5% of Google's workforce is Black. This lack of diversity directly affects the products being built. If the people building AI systems do not represent the diversity of the people who will use those systems, the systems will inevitably reflect the blind spots of their creators. Addressing this requires intentional efforts to broaden participation in AI and to integrate ethics throughout the AI development lifecycle, from problem formulation through deployment and monitoring, rather than treating it as an afterthought.